on this computer. Okay. Okay, so hello everyone. As always, thanks again for joining us today. We are in day 11 of the course, and today is the last day related to SER specifically. So I think it's a nice day because we will see new things, but also we will get a quick summary of all the things that we have learned so far. That you will see that it's a lot. So, but let's start with today's course. So we will learn how to compute response functions in parallel. Okay, so then the idea is that we will use the 3D cube that we created, or we transformed to optical depth a few classes ago, I think day 8, and it was from URM. And then I think the idea is that computing response functions in parallel, so having a cube, I think it will open a new way of exploring the sensitivity of spectral lines. And this combined with state-of-the-art simulation, I think it's a good chance or a good time for start taking a look into this and try to take advantage of both, of being able to compute in parallel response functions or in a simple way, and combine that with numerical simulations that are publicly available and or are easy to get. And we know now how to transform to optical depth and be used in SER. Okay, but the idea is that if you remember, interpreting the response functions was already a bit difficult for one pixel, for one atmosphere, when we did it in the beginning of the class. So I think if you have multiple response functions, it's going to be a bit more difficult to try to give a shape of that. So I mean, try to find a way of properly representing the information containing all that cube. So I think it requires some thinking, but my impression is that probably some of you will dedicate some time to this, and we will see new ways of analyzing the sensitivity of the spectral lines based on those two factors, on simulations and the possibility of computing them in parallel, response function in parallel. Okay, so then let's start with the idea of response functions and the dimension of the response functions. So in day 3, we computed one response function, one atmosphere, response functions to different atmospheric parameters, but with one atmosphere. And at that time, if you remember, the response function was a cube that contained wavelength and optical depth, and then Stokes parameters. And this was per atmospheric parameter. So if we had response function to temperature, we had this cube. Response function to line of sight velocity, we also have this cube, and the same for magnetic field. Okay, so then essentially we had a 2D response function that was wavelength and then optical depth, and per Stokes parameter. So we had 4. So to multiply that by 4, and this per atmospheric parameter. Okay, so now that we are going to compute things in parallel, you will have to multiply that cube by your domain, so your spatial domain. So then it means that your cube could be something like, in this case, x and y, that is the physical domain of your simulation, for example, times wavelength, times optical depth, times Stokes parameter, times atmospheric parameter you are interested in. So then you probably are now thinking that things will escalate very, just 1 second. Oh, yes. So things will escalate very, very quickly if you try to do it just as we did the synthesis of the inversion of the full cube, because it would mean that you will have a cube like this. So it will be 500 times 500 pixels times the wavelength, that at that time was 600 pixels, times optical depth, that is 61, times the 4 Stokes parameters. And for example, if you are interested on temperature, line of sight velocity, field strength, inclination, and azimuth, will be times 5. So you can already get a feeling that this will be really, really heavy or really difficult to handle. So what we have done for the parallel wrap to try to avoid collapsing your computer is first, we restrict the computation, we limited the computation to one atmospheric parameter at a time. So then the idea is that if you run and you have told a CER to compute several response functions, you will only get one. The idea is that the current version, it doesn't stop. So if you have said, I want the response function to temperature and velocity, you will only get one. And this is a bug that we want to fix. So the idea is that soon, the newest version, if you put two, like temperature and velocity, the code will stop. And we said you are asking for more than one atmospheric parameter, and we are not going to provide that. So this is something that we will add later. But the idea is that right now, if you're running, just be sure that just select one parameter. For example, temperature or velocity or inclination. Okay. Then we also strongly recommend to go one blend at a time. So if you remember in the previous classes, we were combining iron, so the iron pair, iron lines in the 630 nanometer range, plus one iron line in 1.5 micron. And the idea is that in this case, you can do it, so the code will not crash, but it's getting bigger and bigger. So my advice is just go one spectral line or one spectral blend at a time. So then things are more easy to handle. But in principle, you can do it. You can add multiple lines. And in this case, the code will do it properly and it will be safe. It's just that the cube will be much bigger. Okay. So then let's start with the class. Then we will go back to the presentation. So today's class, we will have this folder that is the master folder that we have used in the previous classes for inversions and synthesis. But now I just put this subscript as I say, response function, but it's the same concept. So inside, it means that you have your initialization.input file, the Python related procedures. Then you will have run files that we will check now what we need to put there. And then we will run it here. Okay, so then if you open the initialization.input, you will see that it's the same that we were using. So you have to provide a number of cores. Then here you have to provide your input, that in this case, you see that is the same input that we computed in day, I think 8. So it's a 500 times 500 pixels snapshot that was cleaned in the sense that we removed the pixels that didn't provide a reasonable optical depth, and then interpolated to a uniform optical depth. So this is the same one that we use for the synthesis in the previous classes. Okay. And then in this example that I'm going to run now, we are just going to compute 3 times 3 pixels, 9 pixels, the response function for that. And then here, this will not affect, and this also will not affect because this is related more for the inversion. And this one, it will affect. So if you put here a number different than 0, the response function, so I mean, the atmosphere will have a microturbulence value, and then the response function will be computed based on an atmosphere that contains that microturbulence value. In this example, I just put it 0, but in principle, this will affect also the computation of the response function. And then just the location where your CER distribution is. Okay, so then what are we going to run? So if we go back, let's go back. So run files, as always, is just the grid file and the control file. And then in the input files, the lines and the abundance. So let's go to the control file, that is this one here. And if you remember, the way of asking for response function was to put -1 here. So 0 is synthesis, numbers above 0 means inversion cycles, and then -1 is computing a response function. And then profiles, it is fine, we need to change these. And then the grid file, yeah, we will check it now, and this is the same as before. We put 1 here, but I think it doesn't matter for the computation. I think for the computation of the response function, just in case, you can put just 1. And then here, as I said, just put 1 on one given atmospheric parameter. If you put 1 in another, it will run, it will not crash, but it will save just 1 atmosphere. And I'm not sure now which one is, if it's the temperature, or for example, in this case, if I do this, is magnetic field. But I will discuss this with Ricardo, and then we will put a warning that will says I cannot run with this configuration, like 1, 1. So then just be sure that just put 1 for now. And then the rest of the things we don't need to change it. So for the example that we will see later in detail, I decided to compute the response function for the full cube. And this is very, very large. So I decided to try to simplify a bit the size. So then what I did was, first, I'm going to focus only on one blend. So these are the iron lines in the visible. And then also I reduce a lot the spectral sample. So we moved from 10, that was the one that we were using before, and I think is a very good value, to 40. So I think this is not a good value, but just for illustrative purposes, I will just show it with this. But my recommendation, and as you will see later, is to increase a bit spectral sampling, at least 10 or 20 milliamps is much better. Okay, so then let's just check how it will run. So if we try to run for these 3 pixels, and we are here, so we do Python 3 and then this, then the code will run, and it will be very fast because it's like a synthesis, and here the information is just the position and then the time. Okay, and then what you get is that if you go to results, you will see that this is different. So forget about this one for now. You will have this file, okay? And then this file, now we will check how to read it and what is inside. But basically, you have just one output, that is a response function. Okay. So then, as I said, I did it for the full cube. You will see that I have everything here. I have config. So this inside, I always try to put inside each run the configuration, the exact one I use. So then you can check it how I did it. And as I said before, even degrading the spectral sampling 4 times, the cube is 12 gigabytes. So just when you try to do big computations, or I mean, a bigger field of view, just I think try at least a small patch first to get an idea of how big it will be, because it will escalate very, very fast with the number of optical depth points and the number of wavelength points. Okay, so then let's read what we have. Let me just put a stop here, and we can check results, then run one. Okay, so if I do this, we will check how the response function looks like. In this case, I will also do some processing of the results just to give you an idea of what things I believe you could try for try to visualizing the information contained in this cube. And as you can see, it says that it's 500 times 500. Now it's 51 because this is the number of spectral points that we have reducing the spectral sampling. 61 is the number of optical depth points, and then 4 is the number of Stokes parameters. Okay, so yes, so this is what we said. So then in this case, when you are reading it, it's only saving the response function information, but I will talk to Ricardo to also include as an extension, as one for the case of synthesis and inversion, the wavelength vector. So then you can know which wavelength exactly corresponds to the response function domain, the optical depth vector, so then you can also have it there, and the index. So just to be sure that you are, if you included a blend, for example, just to be sure that which points of the total cube correspond to one spectral blend, to one blend or to the blend. Okay, but for today, as I didn't want to push Ricardo to fix all those things in one day or today. I'm just doing it by hand. So I'm just creating the wavelength vector by hand. So if you go to the wavegrid file, you are saying, okay, it starts at -500 and the spectral sampling is 40 and it will reach this point. So then you just create a vector that has a spectral sampling of 40. It starts on 500. And as you know from the cube already, it has 51 spectral points. So I created by hand. And the same for the optical depth. So you know, you can read it from the cube. I put it here an example. So just read the full cube and then take the first dimension of the cube for any pixel, and you will see that it is the same one. But the idea is that I will discuss with Ricardo to include this as an extension, so that you don't need to do this extra step. Okay, but for today, we will do it this way. Okay, so then the first thing we can do is let's check the response function for two representative pixels. Then first, as always, in the day 12, you will have some figures, and then I'm going to use one of them. So this is the temperature that we use. Okay, this is the full domain that we use for computing the response function. And we are going to check the response function on two representative pixels, one with a strong magnetic field and one over a granule that it seems that it should be, the atmosphere should be very different between them. So in the case of, let's go back, I think the blue one, it's this one. You know, this is the red one and the other is the blue one. So if we go to pixel, this is the blue one that was in the corner. So this is how it looks, the Stokes I response function to temperature. The truth is that it looks ugly, but it's because we choose a very, very, very low resolution spectral sampling. So this wavelength, I think we should increase it a lot. But as I said, this is for just an example. But the recommendation is that if you want to cover the same field of view and you have limitation in memory, so just go small patches, by small patches, but try to keep the spectral sampling high, because this response function, it looks not so good as the one we had from day 8, but it's just as an example. And the same for the pixel. So this, it looks more symmetric. The other one looks like it was shifted, so maybe there was some gradient along the line of sight. But it's clear that the sampling in the continuum is probably fine, but in the line core, it's too low for photospheric light. Okay, but this is how it looks response function and how we compute it. So if you remember, we read the response function cube, that this is what the Python wrap is providing. And what I'm plotting in this example is a fixed pixel with an X and Y position. This is wavelength, this is optical depth, and this is Stokes I. So what we saw is the Stokes I response function for a specific pixel, two perturbations on temperature. Okay, and just for simplifying the plot, I normalize it to the maximum of the same pixel, but this is something that is arbitrary. Okay, so then what can we do next? I thought that I could try to do a test of something that in fact is new. So I think I just wanted to do a test to see how it looks. But my impression is that you should try to start from here and building new things. But it's something that I think we should do with the cube that we get from the simulation. So what I'm going to do is to check where the response function to temperature is highest, or which height, to just try to create a map of heights where the response function of this line pair to temperature is highest. So let's try to go step by step on the program, and then we will see the results, and probably you will get a better idea of what I'm trying to say. So the important thing is that we will cover all the domain. So we will go to the X and Y dimensions that we mentioned before. And the idea is that we are going to repeat what we did in day 3, where we computed the maximum response function for the full wavelength domain and for the 4 Stokes parameters. And with that, we created a 1D function that was height dependent, and where we saw how the response function was increasing in the layers where the spectral lines are sensitive, and it was decreasing where the spectral lines stop being sensitive. Okay, so then what we do is we compute the maximum of the response function to Stokes I, so for a given pixel, Y, so I and J, for all the wavelengths and for a specific height. Okay, this is Stokes I. We do the same for Stokes Q, U, and V. So it's the same sentence, but we are just changing this index, that is Q, U, and V. Okay, and then we create a vector that contains the maximum of the 4 Stokes parameters for each height. Okay, so let's try to see how this will look. Okay, just help. All right. Then there's a stop before, yeah. Okay, so then if we do plot tau max RF, so it will look like this. So this is for just 1 pixel. What we have done is computing the maximum response function for each optical depth point. And you can see that here it goes high, and then it goes down, then it goes a bit higher, and then it goes down again. So it's not smooth, again, because the spectral sampling is poor. So then for the time that you want to really use this for your research, try to increase a bit the spectral sampling, but you get the idea. So this is what we did in day 3. So just compute this overall maximum response function. Okay, so then what I'm going to do now is to compute the height where this overall response function is highest. That is, it will be, for example, in this case, it will be here. So just to get an idea of if we can do something with this. Okay, so then what I'm saying is just take the maximum, compute the maximum of the function that we have plotted, and tell me where is maximum or where is highest. And then I'm just saving the optical depth of that index. And with this height response function will be a 2D array where in each pixel, what we have is the optical depth where the complete Stokes response function, so complete 4 Stokes parameter response function to temperature is highest. Okay, so the program will run. It will take some time, but the idea is that we don't need to run it because I already computed here, and this is what we get. So let's try to visualize again what we are having here. So in each pixel, it's an optical depth position. And what we are finding here is that in some regions where you have pale color, the highest value of the response function, it's located at lower optical depth values. And in pixels where the response function is dark, the highest value, it's much higher in the atmosphere, up to log tau -3. Okay, so then it looks not very smooth, but again, it's because of the spectral sampling. So maybe if we do this with 2 or 3 times more spectral sampling, it will be much smoother. And I think this is something that we should explore. So I don't know what we can do with this. I imagine that you can have an idea of how the spectral lines are moving up and down. And if you do the same with a different set of spectral lines, you can check how they move up and down one respect to the other. So I think there's a lot of room for doing things. But it was just something that I wanted to show you, in the sense that now that you have the cube of response functions, there are a lot of things that you can do for exploring how you evaluate the sensitivity of your spectral lines for a given field of view or for a given solar phenomenon. So this is just an example, but probably you can think of different options, and if I have some of them in mind, probably I will share them with you in the future. So just to give you an idea. And also I combine the previous temperature and this one, so then you can try to give a look and try to see that, yeah, it seems that where these complex structures appear, the optical depth where the response function is high will also change a bit. Then we have something complex here. So it seems that it's something that we need to study, and in principle with better spectral sampling. But I guess this has a lot of potential for studying and for trying to, again, if you are going to compare spectral lines or to just evaluate how much information you can get from them in a given representative scenario, then I think this is a good way for starting. Okay, so then this is essentially the first part. Yes, this is the class. So try to compute response functions, and I will now summarize everything, but very important, keep in mind that they are very heavy. So as soon as you increase the spectral sampling, so this one probably will get 4 times bigger. So maybe just this computation will be around 30 or 35 gigabytes. So just be aware of that. Okay, so then let's go back to the presentation, and we were here. So then, as I always said, try to run the computation of the response function for a few pixels, try to get a feeling of what you're getting, and try to, in fact, play with different atmospheric parameters. I just show you temperature, but in principle, you should try at least line of sight velocity, magnetic field strength, inclination, and azimuth, and then check how the response function look like in different regions. As I said, try different locations, and also try different spectral lines. So you can add infrared lines, or you can add visible lines, or different lines of interest. Then, as I said, one extra thing that I think together we should work on is how to visualize all this huge amount of information. And my advice is at least try what I did, but increasing the spectral sampling. And if it's still not very smooth, maybe try to increase a bit the optical depth sampling. Although I would say that probably that's enough, but the main issue is the spectral sampling. And try to get a snapshot like this one, but with a smoother spatial distribution in this height of maximum height of response function. Okay, so then let's start with well, before that, is there any questions so far? So I think response functions are a bit tricky, but more or less, did you get how to at least compute them and read them?
I have a question. It's kind of a practical one.
Yes.
I noticed in the initialization file, it says that you can give it a list of pixels in a separate file, but it doesn't say what order the coordinates should be in or what format that file should be. Do you know? So if you say in that comment above, it says 2 for reading coordinates from a file called pixelcoord.txt in the run files folder.
Yes, but I think this is for, one second. My impression is that this is for an inversion that you have run, and you get issues with a set of pixels, and then you want to only rerun those set of pixels. So the idea of, so the way of providing the code with the same cube, but telling only to embed the pixels that you had issues, I think is this through pixel coordinate, but I'm not sure because this is something that I haven't tried.
So you don't know if it'll work with response functions?
No. My impression or my advice is that you should play with this one. So if you know that, for example, in this case, this one was 250 times 250 pixels, the red triangle. So then if you are interested on that area, I would just set 240, 260, and then 240, and then 260. And with this, you are computing a cube 10 by 10 center on the area of interest. Is this the same you're trying to do?
Yeah, I think that's what I'll do.
Yes, I will start with that because I'm not sure how the PIX coordinate work. I think we should explore that. Maybe I will discuss it with Ricardo and I will explain it in one of the future classes. But my impression is that probably you should just try this one. So just if there are some regions of interest, try to cover it with some context or like 10 pixels around or like 20. And then with that, you will have small patches and they will be centered on the region of interest instead of just having one pixel or two.
Okay.
Okay, but I will check it. Just let me take note of that and I will check it with Ricardo. Because I think he initially created that as a way of allowing the user to repeat the inversion of just random pixels that didn't converge without really needing to repeat the full inversion. So I don't know how it's created and which format you need, or if it's columns and which one is X and Y. So I'm not sure about that. But I will check with him. Okay. Okay, so any other question? Let me put this back. Okay, so then let's jump to the summary of the course, very quick summary. So we have learned how to use SER. We first started in serial mode, so just one pixel at a time. And we learned how to compute response functions and hopefully how to interpret them, at least in a very general way. We learned how to make synthesis and how to embed profiles from that synthesis. You remember we added some noise and we did some tests. And also we learned how to take an atmosphere for a given cube, in particular a simulation that they are now, as I said, they are evolving very fast and they are getting better and better. So I think it's really the time to really push using them and use them as a support for anything, for defining instruments, for checking the capability of the spectral lines, or a lot of things. So then we took the original one that are usually in geometrical height, and we know the gas pressure. This is something that usually we have. And from there, we computed the optical depth, the continuum optical depth at 500 nanometers. That is the one that we use for SER. And then with that, we can do the synthesis and from there to the inversions or compute response functions using those atmospheres. Then we jumped to the parallel mode and we did exactly the same. So we learned how to compute response functions today. And we did synthesis and we added noise to the profiles and we did inversions. And also we did the transformation in parallel. So then everything is much smoother. Okay. But during the way to do those things, we also learned some tips for, I think, improving or getting a better accuracy on your inversion, on creating atmospheres that are representative of different scenarios and also different combinations, like having positive velocity or negative velocity, or an inclination that is below 90 degrees or above 90 degrees. So those combinations will allow the code to go through different possibilities for finding a chi-square that is better probably than the other, that if you have only one atmosphere. Also, we learned that how we take filter graph data that is usually characterized by a non-uniform spectral sampling, and how to adapt that for SER, and also will be the same for design. The main concept was that you need to create an array of intensity or Stokes profiles that has a uniform spectral sampling. This is interpolating the original one, but then you mask the new points that you have added, so the code will not consider them during the inversion. So essentially you are just considering the original information, but you have reformatted the input to be used in SER and desire. We added the wavelength calibration, but as I said at that time, it's just one way, but probably you can do it in different ways, in particular using the atlas. But the key thing is that you need to have a uniform wavelength sampling, because by the time the code will do the convolution with either macroturbulence or a spectral PSF that you provide, the code need to have a uniform spectral sampling. So then, as we always will do some of them, either macroturbulence or spectral PSF, then essentially you always need to have a uniform spectral sampling. Okay, so my impression is that all of those things are a lot of things. So I think we have covered a lot, and I hope you are learning a lot. At least I'm having fun. Okay, so then things that are going to be a bit different from now is that I will distribute the tutorials in different folders. Just let me go back. So if you remember, we had figures here. So the idea is that the folder that I always share with you is this one. And before it was like this. So now I'm trying to organize a bit things. So now we will have separated by codes. So we will have SER, RH, desire. And inside SER, we have the same information as before. So days. I also included in a separate file the source code. And the idea is that we will do the same for the rest of the code. So when RH time comes, we will have different days here, and the same with the desire. And also, I'm including the newest version of the Python wrap. In this case, is the one that we use for SER. The one for RH is a bit different. And I'm putting the date that we have. So today's course is this one. But as I said, I'm already thinking to discuss some things with Ricardo. So then probably I will add a new folder soon, and I will try to add some note about what things were added from before. So then we will have some version control. So Ricardo has it, but I think I've been asking him a lot of things in a very short time. So I think he has not been able to really write down all the changes. So I will try to do it here, and then this will be also translated to the GitHub or GitLab, I don't remember which one is, location where he has the code. But the idea is that now the folder that I always share with you is this one. So you will see that it's a bit more organized. So then, as I said, you will have also the code, the most recent version of the code. If something changed, I will try to add an explanation, not only for the Python wrap, but desire, that is the one that is evolving much quicker than the others. But it's good that we are now with SER, and we will have time with RH. And then recordings will be always inside the number folder. But I wanted to discuss with you that some users told me that it could be also more comfortable to have the recordings in another platform. So for example, in YouTube. I think for me it's fine, but I don't know, what do you think? Maybe we can discuss it today, or maybe you can tell it to me by Discord. So for example, from today's attendant, is there someone that says, no, I think it would not be a good idea to have it, for example, in YouTube?
Okay. We do this for our level 2 workshop courses as well. So
Okay,
I think it's a
fine.
good idea. It's a good idea, yes.
Okay, okay.
Yeah,
So
I
then,
think it's a good idea.
okay, okay. So then I will just learn how to do it, and then I will create a channel, and then I will upload the videos always on the Dropbox folder, but also on YouTube, and let's see how it goes. I think the main issue is that probably you need to download the videos from Dropbox to see them completely. And if they are in YouTube, I think this will simplify the interaction. So, okay, so then I will do it. Okay, so then next class, as I said, we will start with RH. Okay, the truth is that I think in general, concepts and explanations will be a bit more complex because we are getting into non-LT region. so I think it's going to be a bit more, but again, I will try to go slowly, covering the simplest things that you may have questions about it. So then don't worry too much about it. Non-LT is difficult, but still we will try to go step by step. And again, the main target here is to understand how to run the code, how to put things inside the code, and how to understand the information, but we may not enter on really the things behind the code. So the physics behind, I think we probably will not enter there. So don't be scared. So it's okay. But let's see how it goes. And then the question, so when will it start? We will start. The idea is, as I said, all the time, I'm really enjoying giving tutorials. I like being here, discussing with you, hearing your questions or your comments. But I've realized during this period that it's not so easy to prepare the material for the class, to find and fix issues where I'm preparing the material, and then revise the material the day of the class to be ready. So I think I cannot do this at the same time for much longer. So then I think what I'm going to propose you is that I would probably use the next 3 or 4 weeks to prepare most of the things that we are going to cover in the RH course. So in that sense, I can just go through new things that have appeared since I was heavily using RH. Also, I will be able to, if I find an issue, to contact Han and tell him, okay, it's fine if you answer me in 3 days, you don't need to answer me today. And the same with Ricardo. So I think this will allow us to go even deeper and more relaxed over the classes. So essentially what I'm going to propose is to just have a break for preparing the next course, and then meet in 1 month if you agree. So in 4 Fridays. Okay, is it okay for you? I think probably yes.
Yes.
Okay, good. So then before I stop sharing, is there any question or comment or something that you want to recommend me to do or something before getting into the next course?
I would like to just mention that I'm really happy for this course because this was my first time doing the Stokes Inversion. So I'm like doing like a lot of testings and trying to understand and get deeply about it. So I really appreciate it. So thank you so much, Carlos, for that.
Okay, thank you. Okay, thanks. Yes, let me stop sharing. So, okay, so then shall we finish today's course? Yes. Okay. So then thanks a lot, everyone, and see you in 1 month. Okay.
Thank you.
Oh,
Thank you, Carlos.
See you.
Thank you.
bye.
Bye.
Thank you, Carlos. Bye-bye.
Bye.